we present ClutterGen, a cluttered scene generator for robot learning. Creating a simulation environment from scratch is very hard. Objects can collide with surfaces, fall due to gravity, or become unstable as their numbers increase within a limited space. In this case, generating a randomized yet stable object layout becomes exponentially difficult using traditional procedural content generation algorithms. To fix this, expert engineers need to adjust each object's pose manually, which is time-consuming and inefficient. ClutterGen simplifies this process. It's an autoregressive scene generator that creates physically stable and diverse cluttered scenes without needing expert intervention. Here's how it works. First, a supporting object with a fixed support surface is placed in the simulation as the initial queried scene. A list of queried objects is given for placement. To improve the diversity of the generated setups, we randomly shuffle the objects list at the beginning of each episode. After that, a queried object is popped out, and the queried region is updated by the dimension of the scene and the object. The object can be placed in any place within the region, through 3D translation and Z-axis rotation. We sample the points cloud for the object and the scene as the observation for ClutterGen to execute the placement. If the object is not stable, such as bumping or dropping, its movement trajectory will be recorded and used for the next attempt until it gets stably placed. After that, the next object is ready to place. The queried region and the points cloud observation will be updated for the new placement. This iteration is repeated until all objects have been placed stably. We train ClutterGen using the PPO algorithm. The implementation details can be found in the paper. ClutterGen can be directly used to generate cluttered scenes with varied queried regions, even if it was fixed during training. We tested it with translations, rotations, and other changes, achieving over a 75% success rate across 500 trials. We also applied ClutterGen to 10 different tables, generating diverse and interactive setups among all 5 groups. These setups can be used for various robot policy training. To show ClutterGen's real-world applicability, we designed a clutter rearrangement task. The goal of this task is to rearrange the queried objects to user-desired setup. To do this, the perception system first detects all objects that are on the table. Our agent, ClutterGen, will propose 10 new setups for rearrangement. The user can select and confirm a desired setup using the keyboard. The Panda arm will start rearranging the table to match the user-selected setup by detecting, grasping, and placing objects. This iteration is repeated until all objects get rearranged. Success is counted if all objects are rearranged to the goal setup without any collisions or unstable poses. We saw a 70% success rate in 10 episodes. ClutterGen also works as a synthetic data generator for training robots in stable object placement. Using ClutterGen-generated data, we trained a policy deployed directly on a real robot. In each episode, the robot arm grasped and lifted a queried object, while 6 to 8 other objects were randomly placed on the table to form an unseen clutter. The policy predicted a stable placement pose based on the scene points cloud captured by the camera, and the pose is then used to plan and execute the robot's actions. We repeated this process by randomizing the clutter configurations for 5 episodes in 1 iteration per object. Across all 50 episodes, our zero-shot sim to real policy achieved a 72% success rate. Common failure modes of clutter rearrangement and stable object placement tasks include inaccurate placement proposals, camera offsets, and grasp or placement collisions. Thanks for watching.